All right. Well, thanks everybody for being here. And I want to welcome you to the call today. My name is Wyatt Merrill, and on behalf of the U.S. Department of Energy, I want to welcome everybody to a presentation followed by a question and answer session on panel capacity and breaker space in U.S. homes. I'm a technology manager with the Building Technologies Office at the Department of Energy, and I've been the federal lead for the research that you'll hear about today for the past several years that it's been conducted. Um, Back when we first selected this in 2021, we solicited applications from our national labs, and we knew at the time, we being the DOE, knew at the time that building wiring, load centers, transformers were all bottlenecks to new loads and also major affordability issues for consumers when it comes to certain types of renovations and retrofits. But what was still sort of an open question at the time was the severity of that bottleneck. There were a couple of white papers that you could reference on panel capacity for a few hundred homes in certain regions, but nothing really comprehensive. And so we set out to do something that was comprehensive in terms of the characterization of panel capacity in the US building stock. And we wanted to do that on a platform that other researchers and program planners can now use for their own work free of charge. And that's what you hear about today. We knew that these capacity constraints were not only affordability issues that for the homes that they impact directly, but also in aggregate have impacts on utility distribution planning and essentially the rates that everybody sees for electricity. Um, and at the same time, we've seen the number of commercially available technologies that directly address the panel constraint issue, if you will, have grown a lot, and that's been really exciting to see. There's several innovative solutions for building owners that can change what we would consider business as usual when it comes to the need for electrical service upgrades and growing recognition among planners and contractors that these solutions are affordable and reliable. Um, the webinar today is going to focus primarily on the modeling tools that Lawrence Berkeley National Lab and the National Lab of the Rockies have developed in ResStock to characterize panel capacity, both in terms of in the US, both in terms of available breaker slots as well as headroom for ampacity of the panel. I just mentioned the knock-on impacts for distribution planning and the growing number of technology solutions, not so much as a topic for today, but just because I think the tools that you'll hear about today can be brought to bear on a wide variety of remaining research questions and a lot of different real-world applications. These are not just abstract, academic tools. I think there's real-world impact that we're seeing and that you can use these in a lot of ways to evaluate the impact of new technologies and program initiatives. So we may broach those topics in future webinars with this team, or on the other hand, I'm hopeful that members of the audience here will do the same. And if you do, please invite us to your webinar. But without further ado, I'm going to turn things over to Sean Murphy of LBNL and Lixi Liu of NLR, and the broader team of researchers who will be available at the Q&A session will be online as well. So thanks very much for joining us. And Sean, off to you.
All right. Thanks so much for starting us off, Wyatt. And thanks everyone for joining the webinar today. We really appreciate everyone's interest in this work. Before we go into the meat of the presentation, I just want to thank all of my co-authors on this paper, both from Berkeley Lab and from the National Lab of the Rockies. Everyone's been really working hard to bring this work together. So Lixie and I will be primarily speaking today. I just want to thank everyone. One housekeeping item I just wanted to mention is that we do have a Q&A option so people can submit questions um, that we'll answer at the end. So if you look on the bottom of your sort of Zoom bar, you'll see a Q&A option. So you can submit questions anytime throughout the presentation. So today we'll be covering some of the key elements from our recent paper on electrical panel capacity, breaker space, and loads. We're going to start with an overview of why we pursued this research, then move into an overview of our methods, and then we'll spend some time reviewing the results on panel capacity, breaker space, and panel headroom. After that, we'll show you where you can access these data and close with some key takeaways and thoughts on future research. So, what do electrical panels do and why are they important? They distribute electricity to buildings and maintain electrical safety by preventing overloads. Each electrical panel has a rated capacity measured in amps that determines how much load it can safely serve. Electrical contractors determine this rating using load calculations from the National Electrical Code, or NEC. Each panel also has breaker spaces that connect individual circuits to the panel. When we add new loads to homes, it's possible that the home may require to replace that existing electrical panel with a larger one. This can be costly and delay home improvements. Typical panel replacement could be a few $1,000s, which can be a prohibitive cost, but it can be higher when there may be a requirement to increase the size of electrical service provided to your home, or if there's any additional work required to move a panel. So these can be expensive endeavors. Importantly, the lack of panel capacity or breaker space can trigger a panel replacement. In order to understand the homeowner and grid impacts of adding new loads to home that Wyatt was talking about, it's really important that we have strong data on electrical panels. That data has, however, been limited in the past, and this research is intended to address that gap. I'll now walk through some of the important elements of our methodological approach. I'm going to keep it somewhat high level for now, but we'll gladly address some of the specific technical elements of our methods during the Q&A. In order to estimate electrical panel capacity and breaker space across the country, we developed some predictive models using field data on housing characteristics. And then we applied those models to a representative database of single-family homes, ResStock, which is a tool developed by our colleagues at the National Lab of the Rockies. The figure to the right shows some of that training data that we use for the panel capacity model. And we have the different panel capacities based on the different colors. So brown is the 200 amp panels and yellow is 100 amp. As you can see, the distribution of each data set is quite different. And much of this data is from the West Coast, but we also had a data set from Minnesota and homes from several more states from a national survey of electrical panels that was conducted by some of our other colleagues at Berkeley Lab. We simulated electrical load calculations from the National Electrical Code using ResStock equipment data. And then we estimated the headroom in electrical panels. That's how much additional capacity they have, or sort of capacity they have to spare to accommodate new loads, by comparing that predicted panel capacity to the estimated load from those NEC load calculations. We did this for each home in that representative database of homes, ResStock. The predictive models are intended to capture the relationship between electrical panels and various housing characteristics. For our panel capacity models, the idea is that we want to relate housing characteristics that affected the NEC calculations to observed panel capacity ratings. So floor area is a direct input into one of the National Electrical Code calculations, and the fuel of different installed equipment, sort of a proxy for the nameplate ratings of different electrical equipment that may be installed. So those were core variables that we used to sort of develop our panel capacity predictive models. We also related home vintage, so the decade in which it was constructed, to panel capacity. And vintage, well, is not an input into the national load calculation. It does capture just different historical sizing practices, which we know have changed over time. Table below, or the bottom of this slide, summarizes some of the variables that we used for the predictive models. Importantly, we did develop separate models for panel capacity for homes that have electric heat and homes that have non-electric heat. And this was to prevent overfitting due to sort of the prevalence or predominance of data from the West Coast. For available breaker space, we related it to panel capacity, floor area, and the number of large loads that occupy those breaker spaces. The idea here is that if you add major electrical loads to a panel, you're going to occupy breaker space. And depending on the panel size, you may start with different amount of breaker space. So we're capturing important variables that may explain how much space you started with and how much space you've used. A key attribute of both of these models is that they are probabilistic and not deterministic. This distinction is important because similar homes can have different panel capacities and available breaker space. So if you have to take a home, say, or you take 100 homes, all built in the 1970s, they all have gas heat, air conditioning, gas cooking, and an electric dryer, you're going to find a mix of panel sizes. We saw this in the field data. And a deterministic model would just say, take the most common panel rating, say 200 amps, and then predict that any similar home would have a 200 amp panel. But we know that there's all this variation in the building stock, and we wanted to preserve that in our predictions. So we basically estimated the probability that a home has a certain panel size based on its characteristics, and then randomly sampled from those probabilities to assign them to individual homes. This image sort of illustrates that process where on the left we have this distribution of panel capacities, and then we sample from them when we're assigning it to an individual home. So in this case, there's a 40% chance in this, our hypothetical example of a 125 amp panel, and we assigned it 125 amps. But 30% of the time, we'd assign 150 amps, 20% of the time, 100 amps, and so on. So the idea here is just we know there's a lot of diversity within the building stock, and we're trying to maintain that when we're making our predictions nationally. As I mentioned earlier, we estimated existing load using two load calculations from the 2023 National Electrical Code. This first method, which is referred to as Section 220.8.3 or the load-based method, is most common, and it basically tabulates individual loads. It has some default assumptions for the load associated with lighting and branch circuits that serve laundry and kitchens. And it also applies these demand factors to individual loads that are kind of approximating, coincidence on a peak day. The code is recognizing that you're not using everything in your home at the same time and applies this factor to sort of account for the degree of overlap in those loads. The table on the right side of the slide illustrates this process where we have the sort of a default assumption for the amount of power used per square foot with lighting, default assumption for the power used for each branch circuit, then the nameplate ratings of the different loads that are in the home, and then sort of summing those all together while applying that demand factor, which is approximating the coincidence of those loads. The second method, Section 220.8.7, or the meter-based method, uses interval metering data. So it estimates sort of the existing coincident load as 125% of the metered demand from the previous year. I believe 15-minute or 60-minute load is eligible here. We used 15-minute data in our calculations. So to summarize, we developed some predictive models of panel capacity and available breaker space using field data on a range of housing characteristics. That's the process we show in the blue here. We then applied those models to a representative database of homes to estimate panel capacity and breaker space nationwide. That's the orange section of the diagram. Then we simulated the NEC load calculations using data from ResStock, and then for each home, compared panel capacity to the load calculations to determine the amount of headroom, sort of the remaining capacity in those panels to serve new loads. And that's the green section of the diagram. I do want to mention some important caveats to our approach. We don't have perfect information on all of the homes in our field data. We don't know every piece of equipment. We don't know their nameplate ratings. We largely are knowing what the large things that are installed and the fuel used to serve those loads. The data were weighted to the West Coast, but we did mitigate that by developing or mitigated potential overfitting by developing these separate panel capacity models for homes with electric heat and non-electric heat. Interpretations of the National Electrical Code may differ across different authorities having jurisdiction or different users, though we think that our interpretation is generally applicable across the country. We also made some simplifying assumptions on the nameplate ratings for different equipment. Of course, there's going to be different models of each type of equipment installed in the home, but we had to find the ones that we thought were most likely. And then finally, ResStock's sort of approach to representing electric peak demand has not been fully validated with electricity metering data. Okay, now on to the results. In this figure, we show the distribution of panel capacity and how it varies by building vintage, vintage being the decade of construction of the homes. As a reminder, what we're seeing here is the result of applying our predicted models to the representative database of homes. These are not empirical results just from the field data themselves. The horizontal axis on this figure is showing that decadal vintage, and the vertical axis is the share of homes. This format is going to largely apply to the following figures. Each color is representing one of 7 panel capacity bins. The 2 ones to focus on are going to be the one in yellow, which is the 100 amp panels, and then brown, which represents the 200 amp panels. They're the most common panel sizes and sort of demonstrate, or rather, that's where we're going to be seeing the strongest trends. What we see here is that there are more 200 amp panels than 100 amp panels in most vintages, and that the prevalence of 200 amp panels is actually increasing as homes become newer. We expect and do find that 100 amp panels are sort of more common as homes get older, but there are still a lot of 200 amp panels in old homes. That does suggest that homeowners have probably replaced their original panels to accommodate new loads and home retrofits. The home is built in the 1960s. People have been adding things to it for decades, very possibly air conditioning, which may have been the driver for getting a 200 amp panel a few decades ago. I'll also note that panels larger than 200 amps and smaller than 100 amps are pretty uncommon overall. So next we show panel capacity and how it increases with home floor area. As the figure on the right shows, the share of 200 amp panels is increasing as we increase the floor area bin. The share of 100 amp panels declines accordingly. This result aligns with how we would expect the NEC to size loads in larger homes. And larger homes have more circuits, they have more lighting, and they require larger HVAC systems. So the NEC load-based method, as we showed in a few preceding slides, also takes floor area as an input for estimating lighting and plug loads. So this alignment is just sort of an indicator that like, our model is picking up on sort of the expected behavior of the National Electrical Code as it applies to the building stock. Next, we'll show how panel capacity relates to the number of major electric loads in a home. So the horizontal axis of this figure is showing the number of major electric loads, which for the purposes of this calculation are just defined as electric space heating, air conditioning, electric water heating, electric cooking, rooftop PV, electric clothes drying, and electric pool or spa heating equipment. We find that panel capacity increases with the number of major electric loads. So for homes that have 5 or more loads, 90% or more have 200 amp panels. That does sort of align with expectations because the more electric loads that a panel needs to serve, the more capacity that panel is going to have. Although we do see certainly after that 3 major electric loads, there is sort of a sizable increase in the share of the 200 amp panels. So here we take a look at how panel capacity changes with the percent of area median income. So in the figure, the share of homes with 200 amp panels increases from 48% to 60% from the lowest to the highest percent of AMI bins. That's moving from sort of left to right in the figure. Interestingly, our predictive models did not include an income variable. There are some data sets that had income variables, but there was not a common field across the data sets. But higher income is correlated with some housing characteristics, such as the vintage of housing and the number of rooms in a home. So basically, our model is capturing relationships between panel capacity and housing characteristics. And there are these existing relationships between housing and income. And our model is just able to kind of pick up on those correlations. When we look at individual data sets, though, we did find some statistically significant relationships between higher income and the higher likelihood of larger panels, and accordingly, lower income and higher likelihood of smaller panels. So those results can be found in the supplementary materials of our journal article. So if anyone's interested in those, I encourage you to check them out. So in the past few slides, we've been looking at how panel capacity relates to sort of individual building characteristics. And now we're going to see how that all comes together across the country. Nationally, we find that most homes, 58%, have at least 200 amps of panel capacity, but that the distribution of those panels varies by state. On the left side, we have the share of homes with panel capacity that are 100 amps or less. On the right, we have the share of homes with panel capacity 200 amps or more. In both figures, red is representing sort of a larger share. So on the left, red is represented indicating the states that have more 100 amp panels compared to other states. Overall, we find that homes in the South are more likely to have panels with at least 200 amps of capacity than are homes in the Northeast, California, and Great Lakes. Still, in many of the states where there are more 100 amp panels or more panels less than or equal to 100 amps relative to the rest of the country, 200 amp panels are still sort of more common. So if we look at Illinois, we estimate that 40% have panels 100 amps or less, but 47% have 200 amps or more. So there are states where 100 amp panels are more likely, but it's still often the case that 200 amp panel is the most common panel size in that state. The state level variation that we observe does reflect some differences in the share of homes with electric space and water heating in each state. Homes in the South have more electric space and water heating than other regions. And accordingly, more of these homes require 200 amp panels to serve those large electric loads. We also note that homes in Florida and Arizona tend to have larger cooling systems than other states do, which contributes to a higher prevalence of the 200 amp panels in those states. So those were our panel capacity results, and I'll now move into our results on available breaker space. So in this figure, we show the distribution of available breaker space is the vertical axis, share of homes, by the panel capacity bin, which is a horizontal axis. Each color is representing a different amount of available breaker space. So one color to look at in particular is blue, which is the zero available breaker space, which I'll mention in a moment. Overall, we find that the 200 amp panels are more likely to have 5 or more breaker spaces. So that's the brown in the pink, than 100 amp panels are. That makes sense. The panels are physically larger. They come with more spaces. So we'd expect that they're going to have a little bit more available space. However, we do find that at least 20% of all panel sizes have, or 20% of all panels of all sizes have no available breaker space. So that means there are 200 amp panels that have no breaker space, and there are 100 amp panels that have no breaker space. As I mentioned, that's the blue that we see in the figure. So issues with no available breaker space are affecting panels of all sizes. So here we have this, we're looking at the share of homes with 5 or more breaker spaces by state. In contrast to our map of electrical panel capacity, we don't see as much variation with available breaker space. The colors or the color contrast is sort of indicating there's some differences, but the range here between sort of the state with the lowest share of homes with 5 or more breaker spaces and the highest is less than 10 percentage points. So it's maybe somewhat misleading. So main takeaway is just there's less variation in the available breaker space across the country. And the reason that we don't see as much variation is that there are these kind of countervailing effects of panel capacity size on breaker space and the impact of the number of electrical loads on breaker space. The intuition here is that you may have a larger panel, which gives you more space, but oftentimes when you have a large panel, you have more loads. So you kind of start with more space, but you end up using more of it. And then in places that have smaller panels, there are fewer large loads, which means you're just using maybe less of the breaker space provided. And as a result, there just ends up being not a large wide differences across the country in the amount of available breaker space. And now I'm going to turn things over to Lixie to talk about panel capacity headroom.
Thank you, Sean. If you can proceed to the next slide. My name is Lixie Liu, and I'll be walking you through the calculated capacity headroom and the new open access ResDoc dataset that contains electrical panel data and NEC load calculation. Here we have the calculated panel capacity headroom. The good news is that most single-family homes already have room to add new loads without a panel upgrade today. These two charts here show connected load in red and available headroom in green across homes grouped by panel size from 60 to 400 amps and sorted by available headroom. As Sean presented earlier, we calculated headroom two ways. The first is the load-based method on the left, which estimates total connected load by summing equipment ratings together and then applying demand factors. The second is the meter-based method on the right, and here we use simulated electricity data from Restock instead of meter data to estimate peak demand. You can see that the meter-based approach tends to show more headroom because the load-based demand factors are generally more conservative in estimating coincidence of usage than real-world usage. A few key takeaways to note. First, headroom generally increases with panel size, as larger panels tend to be less fully loaded. As we can see in the plots, the median connected load ranges from 65 to 102 amps under the load-based method on the left plot, and 36 to about 55 amps under the meter-based method on the right. The load-based method shows median spare capacity to be just over half the rated capacity for 200 amp panels compared to about a third for 100 amp panels. And the meter-based method on the right shows even more headroom, but similar trends across panel sizes. The second takeaway is that about 2% of homes here show a connected load exceeding their panel rating. That is visible as the red spikes on the right tail of each size bin. While some may reflect genuinely overloaded panels, this is largely a modeling artifact due to inherent uncertainty. The service rating was predicted from limited housing characteristics rather than the detailed equipment list and sizes used in the NEC calculation. So the 2% homes do have a pre-existing capacity constraint under this framework and is a caveat to keep in mind when interpreting our results. Finally, both methods here are designed to apply to evaluate whether a panel can support new loads, and they differ in how new loads are added and accounted for. The detail of that will be covered in a future discussion, as the focus today is on the current state of the panels in the housing stock. Next slide, please. Now moving on to talk about the Restock panel data. To support panel analysis at scale, we are releasing electrical panel data for the first time through the 2025 Restock dataset, which is available on the Open Data Energy Initiative platform. Restock now covers all 50 states. We cover all major housing types as before. It includes roughly 550,000 building models. That is about one per 250 dwelling units. This makes it statistically representative down to the county level. Restock metadata comes from national surveys like Census and EIA's Residential Energy Consumption Survey. Major equipment like space heating, cooling, and water heating is sized to code minimums and varies by climate, house size, occupancy, and envelope conditions. So Restock metadata does capture the range of characteristics seen in real life across homes in the US. And for the first time, each Restock model now includes estimates of panel capacity and breaker space occupancy, and this applies to both the baseline, building, and each retrofit measure. For single-family homes, the panel characteristics come from predictive models that Sean just walked through, but for multifamily units, they come directly from the field measurements since the sample size we have were too small to train a model. So the caveat of that is that the multifamily data likely reflects conditions of the West Coast and other regions where most of the data originated. Though we do have a future plan to update multifamily panel characteristics as more data becomes available for model training. You can access the data set through the QR code on the slide. The QR code will come back again, I think, during Q&A. And And when you are there, documentation is available to help you get started. Next slide, please. So what can you do with this data? There are two main categories of use cases here. The first is understanding the current state of panels in the housing stock, just like some of the results we just walked through. You can ask what panel sizes, headroom levels exist across homes in a given city or state. How does available capacity vary by building vintage, housing type, or income level? Where are the homes most constrained today before any new loads are added? The second category is evaluating the impact of energy retrofits, which again is a future topic of discussion, but for those interested right now, Restock also publishes NEC load calculations for each upgrade measure, so you can assess whether a panel has sufficient capacity to accommodate a given upgrade. And with that data, you can estimate how many homes have enough headroom to absorb the new load, how many would face a constraint, and what alternatives exist short of a full panel replacement, such as load management devices or smart panels, for affordability consideration. Restock also preserves detailed load breakdowns, so you can apply your own assumptions like a margin of safety when doing this analysis. Together, this data set is built to support better decision-making, particularly for program administrators designing incentives and utility planners anticipating grid impacts from residential energy retrofits. Homeowners can also leverage the data by finding a model that best matches their conditions, but they should perform the load calculation directly based on their exact housing details when possible. Finally, a general note on Restock datasets. We document limitations and modeling issues that surface over time, and datasets are published annually with new features, such as the one here on electrical panels. We apply any bug fixes that we can and it can also cover different measures. So please check out our documentation for updates. And if you need help getting started, please reach out to the Restock team. With that, I will pass it back to Sean for the conclusion.
All right, thanks, Lexi. Okay, just a couple more slides to summarize some key takeaways and our thoughts on future work before we move into Q&A. We saw most US single-family homes have panels rated at 200 amps or larger, and 31% have panels 100 amps or smaller. We did find significant state-level variation in the distribution of panel capacity, which suggests that the need for panel replacements to support new loads is likely to vary regionally. At least 20% of all panels of all sizes lack any available breaker space, including the 200 amp panels. This suggests that limited breaker space can constrain the addition of new loads in both small and large panels. We also find that most electrical panels have headroom for additional load. So for the median 100 amp panel, for example, there's 62 amps of headroom that we estimated using that meter-based method, section 228.7 in the National Electrical Code. This indicates that many homes can likely support the addition of some new loads without panel replacements. For future work, there is some related research that we have ongoing that we are very much looking forward to share with you all. Some of the key questions that it will be answering are how many single-family homes in the US will require a panel replacement under sort of a stress test scenario for adding new loads, and how many of those homes can then avoid panel replacements using a combination of panel management, alternative technology selection, and revisions to the National Electrical Code. And we're working on that now, and they're hopefully going to be able to share something with you, soon. And we also see some opportunity for additional research, including expanded data collection, and then using or expanded data collection on manufactured homes and multifamily housing, and then using that data to develop predictive models trained to be specifically applied to manufactured homes and multifamily. And with that, we can move into the Q&A and encourage everyone, check out the paper, the data that Lixie mentioned. You can, on the bottom left, we have a QR code for a sign up to our newsletter that allow you to stay up to date on our research, including on the work that I mentioned that'll be characterizing electrical panel constraints and strategies to mitigate them. And then there's also a link to other related res stock research. But thank you, everyone, and looking forward to your questions.
Okay, Sean, I'll start at the top of the chat. We've got quite a few good questions today. The first one is there anything in the electrical code or specification that prevents a panel from having, say, 40 or 50 breaker spots? It seems silly to have to upgrade a panel for the want of a breaker spot. Do we have any knowledge or any comments on that, Sean?
It's a good question.
Or Lexi?
If you'd like to take that one, that's fine by me or Brennan. I think you've been in the electrical code the most lately.
Yeah, I mean, I'll jump in. I'm not aware of any like limitation on the number of breaker spots in a panel generally, or for panels of given sizes. So I would say like that is definitely like one of the possible paths. Like if a project was running into a breaker space constraint, but not sort of an amperage constraint, panel replacement without increasing that service rating is definitely an option, right? Where you could go from, a small 12 slot panel to a new 30 slot panel, for example. So yeah, unaware of any sort of prohibitions in the electrical code against that. So thanks for that question.
Okay, the next question is, did we look into public records to determine panel capacity, for example, using building permits?
Oh, that's an interesting question. For this project, we did not, though there is another research team based in UCLA that did use permit records to develop an approach for estimating panel capacity in California. So that's a sort of alternative approach. One challenge with using permit data to predict panel capacity of all homes is that permits are selecting for the homes that are doing the upgrades. So you may not be sort of capturing data on types of homes that are not doing upgrades.
Okay. The next question is about, do we find that central air conditioning and electric water heating were not associated with panel capacity for the homes that were not electrically heated? Were we able to tease that out? I don't recall.
I don't think we looked to see that the specific correlations between our predictions and some of those housing characteristics. There is a lot of diversity in the homes, so I would bet that there's probably a home that has even a small panel but still has some electric water heating or an air conditioning as well.
Okay.
Probably we did find that in the field data, at least some examples.
And I can add to that a little bit. I think generally water heating fuel is highly correlated with heating fuel. So in places where there's a lot of fuel heating, your water heating is also more likely to be fuel. But outside of those large fuel heating system, you still definitely have AC, which will drive the panel sizes, especially in the north. And this is why we are seeing still some, I think less than about 30–40% of homes in the north that still have large 200 amps panels. It's AC is partly the reason why there's more homes with larger panels than what electric heating and water heating suggest.
Okay. The next question is more administrative, and I think we talked about this at the top of the webinar, but maybe we want to reiterate again. The question is, are we going to share the recording of this webinar with the people that registered to attend? And I think the answer is yes.
That is correct. Yes, we'll be sharing it with folks, so you can share it with colleagues or watch it later.
Okay. The next question is about smart metering. It says, as we think about the grid of the future, affordability and reliability and resilience, to what extent does it make sense to accelerate the deployment of AMI2 or grid edge technologies combined with panels like SPAN on an integrated basis on the utility side in order to enable services like demand response, VPPs, and so on? Do we have any thoughts on the intersection of AMI2, meters and advanced panels, and how they complement one another?
Yeah, that's an interesting question. So as we mentioned, the next phase of our research is characterizing the degree to which might be electrical strains and strategies to mitigate them. There is seems like every couple of months I see a new technology that's designed to help people manage electricity in their homes. They can help you sort of ways to free up breaker space in your electrical panel or to control loads such that you aren't countering as many loads in the National Electrical Code. One example is basically preventing your dryer from operating at the same time as your EV. That just has an impact on how you count loads in the NEC. And smart panels, as this question indicated, this was the one offered by SPAN, are one of these strategies, and it prevents sort of current on the panel from exceeding a certain threshold, and could be a strategy for preventing certain panel replacements, especially if they're really expensive. And in particular, with the smart panels, they have the potential to provide sort of different electricity grid services, we might say. Like they could participate in bulk power demand response. I think SPAN is trying to design these to also address distribution system constraints. So there is sort of a potential value stack associated with certain panel management strategies that goes beyond just what's beneficial to the homeowner. And all I can say right now is I think it's a very exciting topic, and it's hard to say what the final answer is going to be. But I think it's interesting that utilities are examining the use of these technologies to both prevent maybe panel replacements, which could have upstream distribution system impacts, and using them to actively manage distribution system constraints. So the question of what's the best mix of strategies for homeowners and the grid, I think, is an open question, and certainly one that future research should explore.
Yeah. Thanks, Sean. I think you've almost answered the next question, which was asking about the new construction, thinking about smart homes and new homes that have EV chargers, which the person posting the question is saying they see this as a big trend where they are, and how might that impact the sort of analyses we're talking about here?
Well, when it comes to, there more and more, it seems like there are options for EV chargers that have some sort of control capability that they can respond to use signals from the utility to maybe shut off, but also ones that can determine, is the panel getting constrained and can I sort of reduce the amount of load? So those could be very effective strategies if you're adding an EV charger to an existing panel. Although I think with new construction, as we showed with our figure showing panel capacity by vintage in the 2000s and onward, it's largely 200 amp panels. So it's likely that a 200 amp panel is going to be more able to accommodate a large load like an EV charger than a smaller panel.
Okay. The next question is about multifamily, and the question is this study and the data we've shown here transferable to small, that would be 2 to 4 unit multifamily dwellings at all? Or do we think we need to do a separate study that is specifically looking at multifamily?
Yeah, we chose not to apply these models to multifamily because they are different buildings, or different sets of the building stock. But there is ongoing work that we have that may inform that. Brennan, do you want to speak to this at all?
Yeah, I mean, just we've been sort of following on with previous national surveying in single family homes to expand data collection to try to capture some additional sort of panel and building characteristics from both multifamily dwellings and from manufactured homes as well, both of which are sort of relatively underrepresented in the data that Sean presented here. That work is sort of wrapping up, and hopefully we're publishing that in the next 6 months, and potentially it can be integrated into some of the res stock capabilities that Lixi was describing. Preliminarily, the manufactured homes look pretty similar to what we have just reported for single family homes, but we see quite a distinction with the multifamily, where there are a lot smaller dwelling unit capacities, where the 100 amp becomes sort of the predominant mode there. So stay tuned for more updates.
I will also add that the Restock data today does contain estimates for multifamily. Like I mentioned earlier, they are derived directly from the field data without turning them into a predictive model first, due to the sample size limitation. And as Brennan had mentioned, we do have plan to upgrade those or update those estimates using predictive model when more data becomes available. So the biggest challenge right now is data. If we can sort of leverage existing channels of data collection, particularly through national scale surveys, to get information about electrical panel, I think that will substantially improve the way we can model electrical panel and constraints.
Okay. The next question is about looking at the available remaining headroom in panels. Is all that remaining capacity immediately accessible, or is this only unlocked with some sort of load management? In other words, does the current NEC load calculation allow us to add loads up to the headroom, or say 80% of panel capacity, or just say that this is possible with some load management?
I believe that so long as the load is, less than the electrical panel size, then, a contractor could say it's safely can handle the current. Although there may be some professional judgment in that if you're getting close to, if you're at 90% of the panel capacity, it may be appropriate to recommend a larger panel. And Brendan or Lixie, do you want to expand on this?
I can provide one perspective. I think by and large, to understand whether or not the panel can serve new load, you kind of have to look at the whole inventory still and what that looks like after the upgrade, especially if you're talking about the load-based method, because especially when we're talking about replacing from electric resistance heating to electric heat pump, you are reducing or you are taking some loads out. So this calculation really needs to kind of consider what's being taken out as well as what's being added in. And those accounting is going to differ between the load-based method and the meter-based method. As far as like what 80% of panel capacity, I think that's related to the marginal factor of safety that you can apply. I think that is subject to interpretation and maybe I think it's going to be specific to contractor practices and maybe the local code that's adapted.
Yeah, I'll jump in with a quick follow-up. Agree with everything Lixie just said. Fun updates that are in our new 2026 National Electrical Code. You're now explicitly allowed to deduct removed loads from your metered maximum demand if you're using that .87 method. So that's cool. If you were, for example, removing an air conditioner and replacing it with some other technology, like you would be permitted to sort of deduct that air conditioning load. So that speaks a little bit to what Lixie was just describing. The 80% number really is meant to relate to sort of continuous loads. So generally, that 80% would only be relevant if every load on the panel was considered continuous, which is typically not the case. So yeah, consult your electrician on that one. Yeah, otherwise, great question. Other than to say that the headroom values we presented, like they were not assuming any upgrades, right? Those are just the remaining existing space. So they were not sort of like presuming the use of load controls or these other kinds of solutions. We're just saying, what's the existing load? How does it relate to the current rated capacity? So thanks for the
And
great.
I don't know if this ties in exactly to this question, but it is a question I guess I have, or I think I understand the answer. But just to clarify, the way the model works for the accounting here, if you had 5 amps of headroom on two separate circuits, that's 10 amps at the panel level, but you couldn't actually add 10 amps to either circuit. And so is that there's no accounting in at the circuit level in the model, correct?
That is correct. We're just evaluating things at the level of the overall panel, not downstream of that in specific circuits.
Yeah, just the quick follow up. Like the electrical code lets us sort of like oversubscribe a service panel in a dwelling. That's sort of what the demand factors do. We're allowed to connect more load than the rating would suggest because the implicit understanding is that everything is not expected to operate at the same time. So we get to sort of take that accounting and that deduction. So yeah, no individual sort of branch circuit accounting in the model, but yeah, at the service level, the it's sort of allowed that you can add that additional load up to the rating.
Okay. The next question is, are there any plans to continue this work for large multifamily or commercial buildings?
They'd certainly be interested in doing that, especially if data become available. But I think the lack of the data may be a limiting factor there. If anyone here is aware of data on electrical panel capacity in commercial buildings, we would appreciate you reaching out.
Yeah, please let us know. I think if the data were available, we'd like to do it. The next question is a specific Restock question, which is what were the types of electric heating systems modeled in the Restock analysis?
Yeah. Most of this data really comes from EIA regs. So in that sense, we do model everything that is captured in that survey. So that includes electric furnace, boilers, baseboards, heat pumps, those sort of things.
Okay, thanks, Alexi. Another Restock question. It says, it seems that much of the tutorial videos for Restock are limited to the 2024.2 version. Will there be an upload of a 2025 release webinar, um, as has been done in the past? So this is more of a Restock update question.
Yeah, good question. I will have to get back to you on that. At the moment, we don't have any plans to host a webinar. Though if you do have a pressing need, please reach out to our Restock team directly.
Okay. Um, the next question, as it says, is more of a comment, is to say that available breaker space isn't just a constraint for new loads you're adding, but also the addition of PV and batteries for load shifting and peak shaving. Do we have any comments on that observation?
It's a good point, and we did have data on presence of PV and included that in that breaker space model for that reason.
Okay. The next question is about when we talk about adding new loads, what is the typical load that we're talking about adding in amps? And when we think about these, do we know which ones are, say, the largest and most significant of all the new loads that we talk about adding?
Because it can depend on where you live and sort of what your space conditioning requirements are. Certainly, adding a heat pump with backup electric resistance heating can be quite sizable. And there are 60 amp level 2 EV chargers that are large as well. That Lixie, if you want to add more on the HVAC sizing.
Yeah. So I think on the heat pump, HVAC is definitely one of the largest loads because you have to account for both the cooling and also the heating. Even for heat pump, um, how you size the system and how you connect the heat pump with the electric resistance backup, if there is one, is going to significantly change the HVAC demand that's connected to the panel. So that is going to be the largest load. And then Sean had mentioned EV cooking, interestingly, can be quite large. I think you're talking about 8 to 12 kilowatt at a time. Dryers can also be the big ones, but I think by and large is EV, HVAC, water heating, and cooking, I would say.
Okay, thanks, Lexi. Did we assess how often panels are sized to match the utility service connection? And what happens if you upgrade a panel? Do you also have to upgrade the service connection to the utility?
So we didn't have any data on the typical utility service connection to homes. This has been and also a sort of hard to find piece of information. And anecdotally, we'll hear that service connections may be larger than the existing panels, such that like you might go from 100 amp to 200 amp panel, but already have sufficient electrical service. Um, but if you do need a higher electrical service, it can require additional costs. So I think this is an opportunity for additional research to really understand what the sort of disposition of electrical service is on the utility side.
Okay. The next question is asking more of an economics question and looking at the price differences between different fuels, between electricity and other fuels that are available. Did we find that there was any correlation between these fuel prices and panel sizing, for example? Because as the questioner points out, those economic decisions will reflect things like do you what fuel you use for heating, for example, which can be a big load.
Mhm. We didn't look at that specifically, but I think there is a correlation, or there are places that have had historically very low cost electricity. It's easier to have electric space heating. So in the South, that having electric space heating can be economical where it may not be elsewhere, where electricity prices are more expensive.
Okay. Um, One of our attendees wants to know about the QR codes. We've got them on the
Yeah,
screen
we've been
here.
adding them into the chat, so thanks for
And
for pointing that out.
right. So yes, those are being added to the chat as we go along. So hopefully you'll find the QR code that you need in the chat today. The next question is about the NEC, and this might actually be a question for Brennan because Brennan, you've been working on this a lot. Is can we provide some comments on what changes to the NEC calculation methods would help us to reduce the number of panel upgrades that get triggered?
Yeah, sure. So we've been trying to engage productively to sort of reduce these infrastructure costs and code barriers that exist in the electrical code. And a lot of that has been, trying to leverage metering data from lots of existing homes to say, hey, we actually know what the demand is, and how does that compare with the load calculations? So, some important changes in the 2026 code are reductions in the assumed sort of lighting and plug load density from 3 watts down to 2 watts per square foot. That kind of appears throughout the load calculations for residences. The sort of new heating and cooling equipment when using the .83 method is now permitted to be treated at 50% instead of 100%. So quite an advantage there. There's some specific call outs for sort of more conservative treatment of central electric resistance space heating and electric vehicle charging at 80%. So that's a little bit of a notable update. And then let's see, similarly, the .87 method, this sort of metering data method, we sort of in the 2026 code, we're able to update it. I think I mentioned this before, so that it is explicit that removed loads can be deducted from the metered maximum demand, and that you can look at loads as determined elsewhere in the section. So, using like the demand factors and other assumed load values from elsewhere in the code when you're doing those .87 calculations. So those are all, in our current 2026 electrical code that you can see at the NFPA 70 website right now. And currently we're thinking about the future, about the 2029 electrical code, and are trying to get even more sort of great changes that'll help reduce costs and avoid sort of unnecessary infrastructure burdens and time delays that we're all trying to work against. So
Okay.
stay tuned and
So I think we're probably at time here, and we have some unanswered questions in the Q&A. So a question for the team here is, do we want to promise to answer those questions after the webinar is over? And those answer questions will probably appear in the transcript for the recorded version, correct?
That's a good option. I'm happy to stay and answer the questions just for the sake of the recording. I've also added
Oh.
my contact information with these to the chat if anyone has questions they want to send to us afterwards.
We can also try to type out answers for those that have not been answered still yet, since we will have access to the questions after the meeting and can probably share that along with the recording as well.
Yeah, that's what I thought we could do, Lexi. That's a good idea.
All right. Well, it's great to have so many questions, and we appreciate all of them, and we'll do our best to write up some responses to all of these. But I think we can adjourn the call, the webinar at this point, and just thanks everyone for attending. We really appreciate your interest in the work, and just encourage you all to sign up for our newsletter just to stay in touch about upcoming work because we do have, more results down the pipeline. Thanks, everyone.
Thank you all so much.
Thanks indeed.